So hello again, and we are currently working through and revisiting root finding methods and trying to understand the convergence properties of them. So we've revisited bracketing methods, in particular bisection methods. So let's just go through these few slides, just reminding us of that. So a bracket is when A and B bracket the root, and there's at least one root in that gap. Most examples we look at is when there's just one root in that bracket, and that means the function has opposite signs either side of the root, and that is encapsulated by the so-called intermediate value theorem. And that's basically saying the function has opposite signs either side of that bracket. So this was all covered last time. And bisection is a specific example. We start with an initial bracket and we have the distance each time, and then we discard the bit that doesn't satisfy the intermediate value theorem. Okay, so that's where we got to last time, and what I want to do today with you is go through some initial convergence analysis of this method. So as I say, this aim of this method, if we revisit things in this module, we're aiming to make the results more rigorous mathematically, i.e. we want to derive when these methods converge. As I say, that's really where the mathematician really comes into their own in this sort of computational area. So what I'm going to do is go to the board and we're going to work through convergence analysis. It's in the lecture notes. So all of this mirrors my lecture notes very strongly. I'm working from my lecture notes, obviously expanding on it. So we're in section, if you can see it, 2.3.1. You probably can't see it on the camera there, but we're on 2.3.1 in the lecture notes. That's what we're working through today. So I'm just going to move to the board and I'll see you a little bit later. So here we go. Select this guy. And there we go. So we're up on the board now. And what we're looking at is a convergence analysis of bisection method. So what do we mean by this convergence? Well, I started to look at this in the introductory parts, but let's just spend a bit of time defining what we mean by that. So first of all, a method will converge if it converges to the true solution. And so that's the sort of basic thing. The first thing I'm writing down is that it converges in the first place, right? Okay, if that doesn't happen, then you can't talk about how fast it converges. And then secondly, we're interested in if point one, if one applies, then at what rate will it converge? And this is where the convergence analysis comes in really into its own, because it tells you whether the method will converge or not, but also at what rate it will converge. So those two things bear in mind. May seem obvious, but sometimes it's worth stating obvious definitions before we proceed. If we define the error at step n of your method, and we call that E sub n, and that simply is E to the n equals x to the n, your numerical solution, minus the true solution. So that's your numerical solution, any step. This is your true solution. And as I say, in a lot of the examples we look at in this term, we will know the true solution. Obviously, in general, when you're applying these methods, and one of the main reasons why you apply these methods is that we don't know the true solution, but it's very helpful to do sort of, shall we say, initial examples where we do know the true solution and get a handle about how the method works or when it doesn't work. Okay, so that's the idea. There are varying definitions of error. Sometimes you might apply absolute values to these things. So you might put absolute value. Let me just use a cursor. Sorry. Around that, or you might do others. May do a norm. But at the moment, we're just going to do the simple difference between the numerical solution and the true solution. Okay. And in order to do this, we also will define width of the bracket. We're going to call that Wn. And Wn is simply your your two sides of your bracket at either side, so it's your Bn minus An. Okay. So that's these two things we're sort of using when we use error and the width. And what do we know about the width? Well, the width itself halves each time, yeah, because it's a bisection method. So that's Bn minus An, just rewriting from the last slide, but it also is some factor of 2 over the initial bracket. So B naught A naught is your initial value, the bracket of the width, and we know at each time that will halve and halve. So those are the two things. We've got the width of the bracket, which is defined by our method, and then we've got the error, which we need to say something about in order to quantify the convergence. Basically, another way of stating convergence, by the way, another way of stating convergence, is that your error tends to 0 as n tends to infinity. Okay, so that's another way of saying that. See, error is a difference between the numerical and true solution, but so another way of saying that they both converge is that the error, which is a difference, just goes to 0. Okay, so I maybe just concentrate on these key aspects at this stage, because these concepts will come up again and again, whether we're looking at root finding, which you're familiar with, or matrix iteration methods, which you're not familiar with, or even optimization methods. So try and get used to the sort of lingo and the particular notation I'm using at this point, and allow this sort of revisiting these methods. So just a little bit more on the error that I just mentioned. In my notes, my lectures, I refer to E sub n as the error. And this thing, which is the absolute, as the absolute error. Now this is where I've made a stance on, and I've made a particular choice about my definitions. Some books out there might just call the absolute value of error the error beforehand. I just felt it's clearer to do it this way, and that's where I'm keeping it. So as long as I'm clear about what I'm doing, but beware, there'll be other sort of treatments out there in the literature. Now, so we've got these two ideas. We've got the error and we've got the width, but we need to, so in order to understand the convergence of the two, we need to relate them somehow. And this is the point where we do it. Since I may start a fresh page for this because it's kind of a key idea. So we want to relate error and width of our bracket, and this is a key bit of the argument. And now my argument is, since x of n is the bisector at any point, so this could also be substituted for c of n, this x of n here. Since x of n is x of n is a bisector, then we don't know exactly where the error, what the exact value of the error is, but we know some bounds on it, and this is where it relates to sort of ideas in analysis. Sometimes in analysis you talk about the supremum, the maximum value of something as it converges. This is a little bit similar concept. We know that our absolute value of error will be less than half the width of the bracket. So a little diagram will go very helpful here. At any point in our convergence method, we have AN and BN, and then we have our bisector. And we're going to call that's called C of n, but we also call that x of n for our argument here. And say that the root, since the root lives in the left-hand part of the bracket, say it could live in there, right? Say the root lives in there. The worst case is where the root is right up against this boundary, okay? So that's kind of what the worst case. And this is our width. This width is width. This is our width over 2. So we know the difference between the root and the bisector value, x of n. So the maximum value it can be take is Wn on 2. Okay, let me say that again. So this is our half width. This is width over 2, this distance here. And the worst case is when in the root lies completely the opposite end of this domain. It will lie somewhere in there, and it will be there. So the worst case is when the maximum, so the error, which is xn minus our true solution, is simply less than width on 2. So what we're going to do then is, let's write that down mathematically. The maximum value of our absolute value of error then is equal to Wn on 2. This is the key idea that relates the error now to the width. So we're not saying the exact value of the error, we're saying the maximum value of error. So at any one point, where that's the bisector, that's your maximum value of error. Maximum of Edn is equal to the half width. And what we're saying, that is the case when you got the root, your numerical solution is a bisector, but your root is all the way over here in that. So that's the worst case. So we can then say that actually the error is going to be less than that. Or so whilst we can't say anything about the error, specific value of the error, we can say something about the maximum value of the error, and that's how we do it. So we have now, and we know how the width evolves, it halves each time, and we've got the maximum. So we can then start to write down an equation for the error. So convergence analysis is really about an equation for the error. Okay, so we can now write down an equation for En, because we know how the width evolves and we know how the error works. So this is how we're going to do it. So what we're going to do is we're going to substitute the equation for Wn. Okay, on the lecture notes, it's equation 2.3. That's 2.3 in lecture notes into that previous expression. So we'll have our maximum then value of our error equals half width. And of course that equals 1 over 2 to the n plus 1 b0 minus a0. Okay, so that's just substituting in that expression here for Wn previously, equation 2.3 in the notes. So that gives you the n plus 1 down here, if it goes to 2 to the n, 2n plus 1, and you've got a law for your error. But of course, this b0 minus a0 is simply your maximum error initially. So another way of writing this down is that so your max of absolute value of En is Bn minus An on 2, and of course Bn minus A on 2 is just your maximum error. Sorry, that needs to be an n plus 1 in there. Let me rewrite that. So maximum En plus 1 equals maximum value of En on 2. So all we're saying now, the statement is that the error, because we've said it's the maximum value is the half width, it's going to do exactly the same as the width. It's going to just halve at each step, so that the maximum error halves with each step. So returning to our prescription, this method is always going to converge because it's a bracketing method. Remember, bracketing forces your domain to be the side of the root. But now we've also got the second criteria. We've got a rate of convergence. So another way of looking at this is linear convergence, right? Okay, so it's because the maximum error is just proportional to the error. There's no power in there. There's just the power of 1. So this is linear convergence. So actually that means it's quite slow. Okay, so I'm conscious I'm hitting the ideal 20-minute mark for these videos, so I'm going to stop in a minute. In fact, let me go back to desktop where you can see me, and I'm going to get rid of all that scrolling. Okay, and that's me there again. Just sign off for a minute. So what we've made progress, we've done our first convergence rule for bisection method, and we've shown that if we combine the sort of properties of that bisection method with a definition of error or maximum error, we can get what's called a linear rate of convergence. So I'll return to that right at the beginning of the next video, and I'll see you then. Bye for now.